our previous video, we have discussed about enantiomers. So enantiomers were optically active, non-superimposable, mirror images of each other. So what are diastereomers then? Diastereomers are also optically active, but they do not possess mirror image relationship. Please remember this. This is the difference between enantiomer and diastereomer. So let me repeat it once again. Diastereomers are also optically active, but these two are not related to each other as mirror images of each other. So let me give you an example. So here we have say CS3, CS3, and suppose you have your Br and say chlorine. So you have your chlorine, and this has hydrogen, and this has hydrogen. Both the centers are chiral centers. Okay. So this carbon is also chiral because it is attached to different groups, and this carbon center is also what? Chiral, since this is also attached to 4 different groups. Now, this compound is optically active. Now, see. With the same formula, we can have the structure in which, say, bromine is this side on the other side, and here carbon, here we have chlorine this side, hydrogen and CS3. So these two are, see, they have the same molecular formula, but their structures are different. And moreover, both of these compounds are what? Optically active. Now, if you see these two structures, now if you bring this and try to superimpose over it, will it be superimposable? No. Why? Because if you bring this molecule here, this hydrogen will be coming this side and this bromine will be coming this side. That means they are not related to each other as mirror images. They are not superimposable, that's true. How come they are not related to each other as mirror images? Because if you have a mirror here, then this CS3, this Br is this side. Okay, this Br is also here. But this side you have chlorine. But here this side what you have? You have hydrogen. So these two are not mirror images of each other. If it had to be mirror images of each other, then this chlorine should have been this side and hydrogen should be that side. Since these two are not related to each other as mirror images, therefore they are not enantiomers. Now, they are what? They are called as diastereomers. They are known as what? Diastereomers. And both of them are what? Individually, they are active. So, they have given you this example, and certain characteristics are there. The most important part from here, definition with example and the difference between enantiomers and diastereomers. So on page number 12.50, you have the difference between enantiomers and diastereomers. So diastereomers, now you know it, they are optically active, but they are not mirror images of each other. Whereas enantiomers, they are related as what? Mirror images of each other. Now diastereomers, they have different physical properties, whereas enantiomers, they will be having same or similar physical properties. Now, whenever we come to chemical properties, then the chemical properties of diastereomers will be similar, whereas that of enantiomer will be different. So there are certain differences on page number 12.50. Please remember them properly. Now, let's discuss about what are mesocompounds. Compounds. So mesocompounds are those compounds, even then they contain There's chiral carbons or chiral center, but they are optically inactive. Please remember, even though they contain chiral center, okay, they might contain more than 2 chiral center, more than 1 or 2 chiral center. Even then, they contain chiral center. After having chiral center also, they are optically inactive. So let me give you an example. Tartaric acid. Example is tartaric acid. So tartaric acid, the formula for tartaric acid is we have COOH and OH on both sides. Here you have OH, H and H. So if you draw the mirror image of this one, then what you find? You find COOH, OH, H, COH, H, COOH. So both these carbons, see, this carbon as well as this carbon, both these carbon centers are chiral carbons because they are attached to, they are having 4 different groups. And this is the mirror images, and this carbon as well is what? This carbon as well is what? Chiral carbons. It contains 2 chiral center. Even after having chiral center, this form of tartaric acid, is optically inactive. Why optically inactive? Because this part is very important. See, here, if you pass a plane of symmetry from here, as well from here, what will happen? This plane of symmetry will divide this form of tartaric acid into 2 equal halves. Can you see this one? Carbon, carbon. If you consider this as mirror, then you can see carbon, carbon, hydrogen, hydrogen, oxygen, OH, OH, COOH, COOH. That means this plane of symmetry is dividing this tartaric acid into 2 equal halves. That means this molecule, this form of tartaric acid, has plane of symmetry. And since it has plane of symmetry, now what will happen is the upper part will try to rotate in one direction, the lower part will try to rotate in the other direction. Then what will happen? With equal magnitude but in opposite direction, what will happen? They will cancel out each other's rotation. Now, if the rotation of each half is cancelled out by the other half, then this molecule as a whole will not show any optical activity. That means this is optically inactive. These 2 are the plane of symmetry. Plane of symmetry. Okay? And because of the plane of symmetry, what will happen? It becomes optically inactive. Now one point you have to remember here is, in this case, it becomes optically inactive because of internal compensation. So this is optically inactive. This form of tartaric acid is optically inactive. Why optically inactive? Because of internal compensation. Okay? This form of tartaric acid is optically inactive. See, tartaric acid can have another form also. See, instead of this, we could have COH, C, OH this side, and hydrogen this side, and carbon here, hydrogen here, OH this side, and here COOH. Now, this form of tartaric acid, okay, this form of tartaric acid is optically active. Okay, not this 2 form. Here you can't have a plane of symmetry here. You can't have. Why? Because OH is present. Here H is present. Therefore,
Now this form of tartaric acid is optically active, and this is not the meso compound. Meso compounds are the ones which has planar symmetry and which will divide the molecule into two equal halves. Okay, hope this is clear. And here what you have to remember is you studied about racemic mixture. Now you learned about meso compounds. Both of them are optically inactive. But the difference is what? The difference is in case of meso compound, individually it is inactive because of internal compensation, because it contains planar symmetry. But remember, in case of racemic mixture, you have dextrorotatory part and you have levorotatory part. Now whenever they are in equal concentration, 1:1 ratio, they become optically inactive because of external compensation. Because one molecule of lavioform is the rotation of one molecule of lavioform is cancelled out by the one molecule of dextroform. Therefore, they are externally there's inactivity. They are optically inactive because of external compensation. But individually, in case of racemic mixture, individually, only if you have only the lavioform, then that is optically active. Okay, remember. But here, if you take just one molecule also, this mesoform is optically inactive because of internal compensation. So on page number 12.50, again, you have the difference between racemic mixture and meso compound. So you can go through these differences, and these differences are very important. Okay. So I have told you the most important differences. So what you have to remember from today's class? Diastereomers, enantiomers. It's with example. Okay. And the difference between enantiomers and diastereomers. Then we move on to meso compound. Example. We have to explain with example. We have to show the plane of symmetry. We have to say it is because of external compensation. And the difference between racemic mixture and meso compound.